Okay, 3.1, day 1. You guys, some of you have been waiting for this, the derivative, right? I have good news and bad news. The good news is we reached it, the derivative. The bad news is today is the definition of derivative still.
No.
And Monday too. Okay? In fact, we won't see shortcuts for derivatives until maybe Tuesday or Wednesday next week, where you actually say, oh, the derivative of x squared is 2x. Okay? We can't use that yet, but we're getting there. We're getting pretty close. By the end of this chapter, you will be able to take the derivative of all sorts of different things. Brand new stuff for everyone, including inverse functions, inverse trig functions, exponentials, logarithms, you name it. If I write it on the board, you can find the derivative. This chapter will take 2 tests to get through because it's really, really long. Okay? All right, but 3.1, we have to just kind of start with what Newton said, right? To be honest, I'm not sure Newton said it quite like this, but we were asking Newton the other day, what does it mean to find the slope of a curve? And in my little cartoon, he said it was to find the slope of the tangent line at a point on the curve. So if you hear the question, what is the slope of f of x, it's really talking about the tangent line. Okay? So yesterday on my test, I had you draw a tangent line and try to estimate the slope. Most of you did pretty well with that question. Good job. Okay, this is also called the instantaneous rate of change, but you guys know it better as the derivative. Okay, now I'm not sure how you learned derivative last time, but my guess is when you first learned how to use a derivative, you learned the definition, and then you learned that you can get an expression in the end and plug numbers into it. I'm going to kind of take it the other way. We're going to start with the derivative at a particular value, and then we'll generalize it and make it for any and all values. Okay, so the general formula for the definition of a derivative at x equals a is this. It's f of a plus h minus f of a all over h, and then a limo parked out front. Don't forget to park the limo out front. Okay? So this is a derivative. Why does it work? I've gone over several times. Let's do it again real quick. You've got a point at a, comma, f of a. Let's say this one. You've got a second point at a plus a hair, comma, f of a plus a hair. So that's this point. So your 2 points are a comma f of a and a plus h comma f of a plus h. The curve runs through these points. Right? There is a secant line that connects these 2 points. What you see here that I'm circling right now is the slope of that secant line. By the way, this is called a difference quotient, what I just circled. It really just means the slope of the secant line. Okay, then we do a limit as h goes to 0, and what happens is this point, the second point, slowly collapses onto the first point. So it forms a more of a tangent line situation. You have to admit, if h was exactly 0, these would be one and the same point. Okay, so that's your first definition of a derivative. And right now, this limit is a two-sided limit. Okay, so notice this means 0 from both sides. That's what it means. So whenever you see limo, it means limit from left and right. Okay, we're also going to do what's called a one-sided derivative, where we'll use limo plus and limo minus, but that's for a little bit later. Okay? All right, so if this is the function f of x, which it is, this is commonly called f prime at a. Maybe you've seen that before. How many of you have seen the prime there? It's pronounced f prime at a. This will give you the slope of the tangent line at A, which is this green line here. So the slope is f prime of A. What if I didn't want to do a specific A? What if I just wanted to do like any old value of x? Well, you can also just do that if you want. You could do limo f of, instead of like a specific A value, you could just use any x and all x's like this. Okay, so this would be pronounced f prime of x. Okay, so let's move on. Okay, we're going to talk also about domain and like what values of A are allowed and what values of A are not allowed, but that's for a little bit later. Okay, let's try an example. Let's just say you're supposed to use the definition of a derivative. So I call that DOD. DOD, okay, the definition of a derivative. Use the definition of the derivative to find, let's do f prime of 1 and f prime of x. So specifically at 1 and generically at any x. Okay, the function is, for our first one, just simply x squared plus 4. Not very interesting. Okay, so you would run the new, or the definition of a derivative. So you would do limit as h goes to 0. You would do f of 1 plus h minus f of 1 all over h. And this is now called f prime at 1. Okay, you would substitute in your 1 plus h. So you're going to have 1 plus h squared plus 4 minus, and then you substitute in your 1, which just gives you 1 plus 4. And this is all over h. This is 1 plus 4. And we have this limo 1 plus 2h plus h squared plus 4 minus 5 all over h. And after you've done these for a while, you realize anything that has no h is going to cancel out. Which means everything upstairs has an h in it now. You can then factor that h out, as many of you did properly on the test. You can then reduce by division. And this gives us final permission to plug in 0 for any remaining h's. So some of you keep forgetting to park that limo out front, and so you didn't get this last step right. The answer is 2. So you're supposed to make h 0 in the end, if there are any left. Sometimes there are none. But you don't want h in your answer, or you never really collapse the 2 points together. Okay, so what does this mean? The meaning is always really important, right? Don't lose sight of what it means. We're talking about the graph y equals x squared plus 4, which looks like this. We have learned in pre-calc what it means to find f of 1, right? This is the point 1 comma 5. So this is the function x squared plus 4. It's just a parabola shifted up 4. We've known for a long time that the coordinates at that point are 1, 5, but now we know the slope of the tangent line at that point. We know the slope of this line now, see? The slope of this line is called f prime of 1, and it is 2. So we know more about the graph at x equals 1 than we used to. We used to just know, oh yeah, the point is 1, 5, but now we can actually talk about the slope there. And that's very meaningful. Do you think if I were to pick a different point that the slope would be the same, still be slope 2? No. Do you think this is the only point on the parabola whose slope is 2? That's a good question. I think it is too. I think if you were to try to draw any other tangent line, it would have a slope different from this one. Right? Okay. So my question is, why can't we just write down just do like the derivative with all x's in mind? Like, why do we have to pick 1, or 2 or 5? We don't. So let's just do this again. This time we're not going to put any a value in. We'll just call it x and keep it generic, if you get my drift. So now we're going to find f prime of x. So we just run it again. This time we're not going to put any numbers in for a. We're just going to call it f of x plus h. And we have x plus h quantity squared plus 4 minus x squared plus 4 all over h. And I almost forgot to park my limo out here. This requires you to FOIL it all out like usual. And you guys, many of you already know what the derivative is going to be, but let's just work it out. So this is 2xh, we've got an h squared, we've got a 4, we've got a minus x squared, we've got a minus 4, this is all over h, and the fun part, cancel stuff out. All right, so goodbye to anything that has no h. Factor out one factor of h on top, reduce by division, and substitute in 0 for any remaining h's. Okay, so many of you knew already that the answer to the derivative of x squared plus 4 was 2x, because you were taught that you can take the little 2 from x squared and drop it to the front, reduce it by 1 power, and then as for constants, well, their derivative is just 0. But I'm wondering if you know why that works. Because, why not just let you use that? That is so much faster than this. Well, I have one student, first period, who sat down and proved that the derivative of ax to the n is nax to the n minus 1. He actually sat down and did that. He took this and he plugged it into my formula here and showed that this will always be the outcome. I think that student deserves the right to use the shortcut. But what does that thing mean? What is that? What is 2x?
The slope at any point on the graph of f of x is slope.
Right. It's a slope calculating tool. You give me x and I'll tell you the slope of the tangent line. Okay, so somebody's saying x. Ready, go. 5, the slope would be 10. Give me a different number. 42. How did I know that was coming? The slope would be 84, extremely steep. You see what I'm saying? So this is almost better than plugging in a value. This tells you the slope of all the lines. You just have to provide x. And that's what the derivative is. The first derivative's job is to calculate slopes for you. Once you get that thing, you could plug in any x you want, and you'll know the slope of the line, the tangent line. What would happen if we graphed this? So we have the graph of, we already have the graph of x squared plus 4. Right? This is the graph of f. What does the graph of 2x look like? Isn't that just like a line? 2x plus 0. So wouldn't it just be this? Be like this, I think, right? Y equals 2x. This is your derivative. So this is f prime, see? So it's pretty common where in this class what we'll do is not only have the graph of f, but on the same grid have the graph of f prime so we can see them side by side. The y-coordinates on the black graph refer to actual position values. The y-coordinates of the blue represent the slopes at the various points on the black. What are some notations? You guys know what notation means? It's how you write things, right? Because you might have seen multiple ways of writing f prime. Maybe you've seen some of these. First of all, we have f prime. By the way, on the AP test, sometimes they'll write f prime. Sometimes they'll write f prime of x. Right? Sometimes they'll write df dx. Have you seen that one before? Okay. If you have a TI-89, I know you've seen it, because that's the notation that the TI calculator uses. There's also one that looks like this, where you do df of x dx. Same thing, really. I'm just writing my f as f of x. How about this one? dx. That means the derivative also. There's so many notations. Some people don't like using f. They like to use just y for everything, you know. dy dx. I've seen that. And this is an interesting one. d dx f of x. All of these mean exactly the same thing. They mean find the derivative. Or sometimes we say take the derivative. It's like take the derivative. That is the strangest choice of verbs. Where would you like me to take your derivative? I guess it's like take a seat. Hey, everybody take a seat. All right, where do we get to go with these chairs? Okay. Okay. But there are many notations. In this textbook, you probably won't see that one, but you'll see all the others. Okay? All right, the guy who's responsible for the little prime, the one who gets credit for that is Lagrange. So Lagrange used symbols like f prime, f double prime, that's if you take the derivative of the derivative, f triple prime, and usually if we go any higher than 3 derivatives, we write it like this. So f, and then in parentheses 4, that means 4 derivatives. F parentheses 5, that means 5 derivatives, and so on. The guy who's responsible for the d dx notation, you might say, like, what the heck is the d dx, right? Well, let me demystify that for you, because do you guys remember that slope is delta y over delta x, right? You guys know what that means? y2 minus y1, right? Yeah, it means change in y over change in x. So what's going on is we are actually finding a slope. So we are doing a delta y over delta x. But we are collapsing the 2 points so close together, we don't feel like we're allowed to use the capital Greek letter delta. So we use the lowercase letter delta, which looks like this. At least in the English, we stole the delta, and the lowercase looks like this. So what we're doing is a very, very, very small delta y over delta x, where the 2 points are actually collapsed. But it means change in y over change in x is just on the infinitesimal scale. Okay, so it actually is a meaningful notation. Okay, so how do you do multiple derivatives? This, by the way, goes to Leibniz. I don't think there's a T in the name. I think it's Leibniz. Anyway, it's df dx. That's your first derivative. Does anyone know how to write the second derivative? Has anyone seen this? You guys said you saw df dx before, right? Okay, so the idea is first you take the derivative of f, and then you're going to take the derivative again of that. And then you can take the derivative of that. See? So what happens is it looks, on top it looks like d, f, and then on the bottom it looks like dx, dx, dx. So what you do is you write it as d squared f dx squared of f. That's really weird. But it reminds us that d dx was applied twice. Weird notation, but it is what it is, and we use it. And then the third derivative would be, d cubed f dx cubed. And you can put any number of derivatives. So you might ask, well, what the heck is a second derivative? This is a good question. If a function maps out all the different positions of the points, and the first derivative's job is to find all the slopes of the various points, then what the heck does the second derivative even mean? Generally, a second derivative tells you how bent or how curved the graph is. So the first derivative tells you how sloped it is. The second derivative tells you how curved it is. So we'll get to the second derivative more later. The third derivative geometrically is very hard to understand. How do you even understand that? There's a position, there's a slope, there's a curviness. What's left to talk about? What's left to talk about? You need to know that you can take the derivative not just once, but as many times as the problem will allow. Okay, but this is just all notation. So let's move on. In the textbook, they give you an alternative way to do the definition of a derivative. So that you can think of this as alternative DOD, definition of derivative. And it looks like this. You have to know this formula for the AP test, okay? It looks like this. F prime at A is not limo, but limit as x goes to A of f of x minus f of A all over x minus A. This looks different from what we had before. And sometimes the textbook will ask you to use this formula. So what's this formula about? This is what happens when you treat your first point as maybe A comma f of A. So this is the point A f of A, just like before. But for the second point, you just simply call it x f of x. So this is the point x comma f of x. And then the curve runs through. So the slope of this secant line looks a little different now. It's f of x minus f of A for the top, and x minus A for your run. There's no h. And to collapse the points, instead of making h go to 0, you make x go to A. If you change the x to a plus h, this becomes the old formula. Okay? I never use this one to find a generic derivative, but I do use it to find the derivative at a point. Okay? So that's what it's good for. You might actually like it better. Let's try a couple of examples where they tell us to use this formula. Okay, so the instructions will say, use the alternative definition of a derivative. Use the alternative DOD to find f prime at A. And for this one, we're going to do 2 examples instead of 1. The first one will be f of x is equal to x cubed plus 3x. And the A value we'll pick is 2. For the second example, we'll do f of x equals rad x, and the A value will be 4. All right, so let's do the first one. Okay, so let's do a new definition. What's the new definition? F prime is Limska. I know I'm not saying that right. F of x minus f of A over x minus A. The cool thing about this definition is you don't have to substitute in that x plus h. You can just go like this. Just take the original function and subtract off f of A. F of A would just be, in this case, since A is 2, basically it's just going to be 2 cubed plus 3 times 2. The denominator is a little messier. It's not just h. Okay, so let's see what happens here. So we get, oops, I forgot to write my limit. limit as x goes to 2. All right, the limit as x goes to 2 of x cubed plus 3x minus, and then here we have 8 plus 6, which is 14, thank you. Ooh, how do I solve that? Plug in 2. That's the first thing you always try, right? But that's never going to work on a derivative because we are trying to find the slope between 2 points. I think this factors such that the top has an x minus 2 factor, see? So I believe with all my heart that the numerator should factor into x minus 2 times something. If it doesn't, something's wrong. Okay, I will never be able to cancel that discontinuity. All right. How do we factor a generic polynomial? That's right, synthetic division. Okay, so this is a good pre-calc review here. We know that x minus 2 is a factor. That means that 2 is a root. So we put our root here. How do you write x cubed plus 3x minus 14 in coefficient form? 1 for the x cubed, 0 for the x squared, 3 for the x, and negative 14 for your constant. And then you start this off, remember, by dropping the 1 down. That's not even like a step. That's like step 0. Okay, now let's get busy and do our synthetic division. Hopefully you remember this. If not, here it is. You multiply this by the number in the box and add. Multiply that by the number in the box and add. Multiply that by the number in the box and add. We got a remainder of 0. So I was right. 2 really was a root. X minus 2 really does factor. Okay, remember what this means. This means 1x squared plus 2x plus 7. So that's our missing factor here. The x minus 2 cancels out by division. And now we are allowed to plug in 2. So let's do it. So it's going to be 2 squared plus 2 times 2 plus 7, which is 15. 15. The slope of the line tangent to the curve x cubed plus 3x at 2 is 15. Okay? See, I would not use this, though, to find the generic derivative. This is only because I knew I was going to be working at a equals 2. My second example was to do rad x, this time at a equals 4. So let's try that. So we want to find f prime at 4 for f of x equals rad x. Okay, so we'll set up our alternative definition. X goes to a would mean x goes to 4 in this case. F of x is just rad x. F of 4 is rad 4. And on the bottom we have x minus 4. Boy, that looks familiar. Didn't we just do that on our test yesterday? We did. We sure did. This was the conjugate thing, right? The conjugate trick. Okay, so if you FOIL the top, you get x minus 4, and there's an x minus 4 chilling on the bottom already. So this top part foils so nicely, and then this cancels out, and now you can plug in the 4. 1 over rad 4 plus 2, that's just 1/4. I don't know, maybe you don't like this one as much as the other one, but you have to know both anyway. So you have 2 ways of doing the definition of derivative. Take your pick. Remember how a minute ago we did a problem where it was f of x equals x squared plus 4, and in the end we found that the derivative was 2x, and I had them both graphed at the same time. So I had this one and this one on the same grid. Remember that? What are their domains? What are the domains? Well, let's look at f first. What's the domain of any parabola? All real numbers, right? All real numbers. So it should be just basically negative infinity to infinity, right? You can plug any number you want into a parabola. Another thing that's interesting about a parabola and polynomials in general is there's always a slope. Like look at all the points on here. They all have a tangent line. There's no exceptions. So you can see that, look at the derivative. What did it come out to? 2x. What kind of shape is that? Nice straight line, right? What's the domain of a line? All real numbers. So what I'm saying is some graphs not only have y values at every point, but they also have slopes no matter where you wish to draw. You could draw a tangent line anywhere you want on a parabola, and it would always have a defined slope. Okay? Is this true for all functions? Is that true in general? Like, if the domain of the function is all real numbers, then there's going to be a slope everywhere. You know what I mean? Everywhere there's going to be a slope. It's not true. Let's look at the example of sin x. Sin x actually has a slope everywhere you wish to draw it. I wanted to draw this one. F of x is equal to absolute value x. This is a really interesting graph. It is perfectly continuous for all x's. Right? Looks just like this. Good old graph, right? But what does the derivative look like? Just look at the picture and tell me what the slope is. You know what I mean? I mean, these are two straight lines. What's the slope on the right side? 1, correct. So f prime of x is simply 1. That's if x is greater than 0. You see what I mean? That's only for this right side piece. The slope is 1. And that's constantly 1. Everywhere it's 1. It's just a straight line. What about the left side? Negative 1. Right. The slope on this side is negative 1. So f prime of x is negative 1 when x is negative. So this is kind of a weird example, but if you really wanted to write the derivative, you could just write it as a piecewise function. You could say, look, the slope is always 1, no matter where you are on the right, and the slope is always negative 1, no matter where you are on the left. But what about at 0? Seriously, look at the origin, right? If yesterday's test had a question like, here's an absolute value graph, now draw me a tangent line at the origin. Why would that be a totally unfair question? Why is it unfair for me to ask you to draw a tangent line at the origin? Remember what a tangent line is? It's supposed to be the line, one unique line that brushes up against the graph, touching it once, but not passing through. We got a problem. There are lots of those. See that? You have a sharp corner. It's called a corner in math. And that corner allows us to draw multiple examples of tangency. So this is a very strange point. It's well defined, but it doesn't have a slope. So my derivative domain is a little different from my original domain. What is the domain of absolute value x? What's the domain? All real numbers, right. You can find the absolute value of anything. But what is the domain of my derivative? Yeah, everything but 0. Zero is not included. And the reason is I don't know what the slope is. I can't decide. Is it negative 1 or 1? I don't know. Let's draw the graph of both the function and its derivative side by side so you can see them together. The graph of absolute value, piece of cake, looks like this. This is f, right? The graph of the derivative looks more like this. It's basically 1, 1, 1, 1, 1, 1, 1, 1. It's always 1 on this side, and on the left side, -1. Okay, so listen very, very carefully. This point at the origin is well defined, but the slope is not. So what happened to the derivative graph at 0? What happened? What happened to the graph at 0? Look at the colored graph. It jumps. So what we're going to do on Monday, part of our lesson will be, I'm going to give you flashcards, and you have to match up a graph with a derivative graph. And there's a total of 16 graphs for f and 16 graphs for its f prime, and you're trying to match them. Our conclusion on that was the domain of the derivative can be smaller than the domain of the original.